I'm going to talk today about seeking black holes in dwarf galaxies. In this session, a lot of us will be, I'll be talking about black holes. The full mass spectrum will be explored, or at least a lot of it. And my focus tends to be on low mass galaxies. And so that's where I'm going to mostly hang out today for the next 25 minutes of your life. I have a bunch of collaborators. The green ones are some undergraduate students who I've worked with who are super awesome. There's more of my undergraduate students in this room. You should hang out with them and ask them what they're working on. Some of them are back there. There's one here. There's another one on Zoom. He's really great too. We know why he's not here. All right. So one of the main questions that I'm interested in answering is we've got these different like astronomy 101 flavors of galaxies. And we know that the elliptical galaxies tend to have black holes in them, and so do the spiral disk galaxies. And the dwarf galaxies have question mark black holes in them. So for a long time, we thought that none of them did. And then there were like a few weird ones, like, oh, there's two dwarf galaxies with massive black holes. And now that people are actually looking for them, there's a whole bunch. So neat. And so something that is cool to think about is how did they get there? When did they get there? And in particular, are they the seeds to supermassive black holes in massive galaxies? So a lot of people think that the supermassive black hole seeds form in the early universe at some kind of intermediate or medium-sized mass in some sort of really interesting way in terms of physics that we don't have anymore, whatever that physics is. The universe is different now, so we don't make seeds like this, maybe. And perhaps these medium-sized black holes didn't grow into supermassive black holes, and they are still hanging out in our local universe as intermediate mass black holes in small galaxies. And so if you want to know how to build a supermassive black hole, that's actually kind of a problem because supermassive black holes have erased their formation history. There's not a really good way to know if they form from like a giant gas cloud or if they form from a whole bunch of little black holes merging together or some sort of biggish black hole with some gas or some combination of this, because once you've got your supermassive black hole, you can't ask it how it got there. It just is what it is. But if you can find one that hasn't grown, looking at its mass can give you a clue as to how it formed, because there's different models of seed formation that give you different masses and also different frequencies of formation, different redshifts of formation, and all that stuff. So some typical places to look in the local universe for answers to this question are AGN in dwarf galaxies, like this galaxy RGG 118, which is a nice pretty one. It has possibly the smallest measured massive black hole in the center of 50,000 solar masses or so, plus or minus. And then another place to look is off nuclear halo sources. So this blue blob right there is called HLX1. It's a really, really bright variable X-ray source that is quite possibly an intermediate mass black hole in the halo of a more massive galaxy. I'll get back to that at the end. All right. So the tools that I'm going to use to work on solving these questions, I use the Chonga code and the simulations that have yet to be introduced in this meeting, so I'm glad to talk about them. Are a few different sets of zoom-in simulations. These are called the marvelous dwarfs. For zoom-in dwarf volumes, they have only dwarf galaxies in them. They have no massive galaxies. They're named after 4 female Marvel superheroes: Elektra, Captain Marvel, Rogue, and Storm. And then the other 4 simulations are also zooms, but they include a Milky Way type galaxy, as well as the neighborhood of surrounding dwarf satellites. And these we call the DC Justice League, named after 4 female Supreme Court justices: Sandra, Ruth, Sonia, and Elena. Right. And so the dwarf galaxies in these simulations are going to make up the sample that I'm going to talk about for the beginning of my talk today. So we look at the dwarfs in the Marvelous sample, as well as the satellites in the DC Justice League. And a quick aside before I go on is that in my in the appendix of my most recent paper, I actually did an estimate of the carbon footprint that it took to run these simulations based on how many cores we used in our supercomputers and how much time it took to run them. And I estimated that those of us who use these should plant 152 trees. And so I just wanted to give a heads up that our footprint as most of us here are as theorists is not a carbon neutral footprint, and that we should be mindful of that. So thanks for listening. You're still stuck with me. You have to keep listening. All right. So in these simulations, the black holes form at a mass of 50,000 solar masses, and they form from dense collapsing, low metallicity, and low molecular hydrogen fraction gas, which broadly encompasses a lot of the formation models of how we think seeds form in the early universe. It most closely reflects this one called direct collapse, but it doesn't even reflect that one that well because we can't resolve anything in terms of how black holes form. But this is a pretty good guess. One thing that's really important that we do is this dynamical friction subgrid model that Michael Tremmel implemented in this 2015 paper. You can read about this. So because the black hole particle size is similar to that of the surrounding particles, dynamical friction doesn't actually happen in the way it should in the actual universe. And so by adding a subgrid model, does it work if no, I did the wrong button. Okay, there we go. By adding the subgrid model, different black holes tossed into a halo will have their orbits decay and hit the center of the galaxy in a reasonable amount of time, comparable with the Chandrasekhar analytical estimate. And so any black hole that is in the center of the galaxy should be there and will stay there. And any galaxy that is somewhere else, or any black hole that is somewhere else in a galaxy, should probably also be there and is going to have realistic dynamical evolution. In terms of accretion prescription, we use a modified Bondi-Hoyle and some thermal feedback. We've already heard from Arif about how that feedback might need to be modified. And we heard from Ben about how he's going to do super bubble feedback with black holes. And so there's a lot of lots of thoughts going on with all of this stuff. All right, so when black holes form in these simulations, they form in the early universe and then their formation is cut off. And that is because of the criterion of low metallicity gas before the black holes form. So here's time and here's redshift. And for all of the simulations that for Marvel and for DC Justice League, there's this big peak of black hole formation. And then after about 500 million years, it stops, except there's one that forms right there. But for the most part, because of once star formation starts happening, we get metals that propagate and there's no more black holes that form. This is a distribution of the galaxy mass at the time that the black holes form. So black holes form in very small galaxies. The different colors are just divided up by which simulation it is, but you can see the distributions are about the same. So the total mass, the virial mass of these halos is between 10 to the 8 and 10 to the 9 or so, which is a very tiny galaxy. That's not the stellar mass, that is the total dark matter and everything mass. These are very little galaxies, but this is also the halo mass that the direct collapse black hole seeds in the early universe are predicted to form in. And so this is actually consistent with where people think black hole seeds should form. Going to redshift 0 in the local universe, we can measure how many of these dwarf galaxies have black holes in them, and that is a function that increases with halo mass. So as you get to about like an LMC-sized galaxy, you can look at it in halo mass or stellar mass, whichever one you like better, even magnitudes. This is probably not the crowd for that, but you can see that as you get to a larger galaxy, you're more likely to have a black hole. And so little galaxies, not too likely to have a black hole. And then as they get bigger, you're more likely to have one. All of the Milky Way type galaxies do have massive black holes. All right. So here are a couple pictures of the dwarfs that have black holes made with Pi and Bonnie. Thank you for that. And so each galaxy is shown twice, a face-on and an edge-on one. And there's a red cross that marks the point of where the black hole is. And you might notice that not all of the red crosses are central. In fact, some of the red crosses are like not in the galaxy even. It is technically, but it's not in the stellar part. So that's interesting, what's going on there. It turns out that about half of the black holes in dwarf are off-center. So this is a distribution of the distance from the halo center, which is how many black holes you've got. So this big peak here is where there's a whole bunch of them in the center, and that is what we expect for massive galaxies for sure. But then there's this tail, which are off-center black holes. And I will remind you that we do model dynamical friction. And so this is a real thing. This is not a numerical artifact. This is an actual dynamical effect going on. And I will show you how it happens. All right, here is the tail of a wandering intermediate mass black hole. You can see there's a bit of a fuzz here. That's the galaxy at a redshift of 4.8. And I've cartooned the black hole in with a little white circle around it so you can see it. So it's not to scale, but that's our little fuzz galaxy. And if we fast forward in time, oh, it's a little hard to tell. There's a little fuzz there. So it's got a neighbor coming. And then, sorry, our snapshot resolution is not perfect, but there's the neighbor up there. Here's the neighbor. Look, it's much bigger than this little guy, actually, and it does not have a black hole in it. So now we're redshift 2.3. And now we're at redshift 1.5, 1.4. This is when our little galaxy eventually gets enveloped by the larger galaxy. And this is basically what it looks like at redshift 0 a few billion years later as well. This black hole keeps on wandering around the outskirts of this dwarf galaxy. So it was accreted by a larger galaxy, and because this larger dwarf has a core density profile, the dynamical friction is just not very efficient. So we've calculated the dynamical friction timescales for all of the off-center dwarfs. They're all longer than a Hubble time. And so you can see that even though we've got a black hole and there's a nice galactic center right there, there's just not enough stuff on the outside for it to dynamically frict against. And the density profile is chord, so it's flat. And so there's not a deep potential well for the black hole to want to fall into. And so it does work on going that way, just very, very slowly. And so that is the story of these off-center black holes. This is how they become off-center. They start central in a tiny galaxy. They're most likely accreted by a larger one, and then they end up wandering around. So that's the story. Dwarfs can also have multiple black holes. So this is an example of a 10 to the 9 stellar mass galaxy with a central black hole of about 1 million solar masses and a wandering outer one. So you can have more than one in each galaxy, which means they could merge, which I'm going to get to later. These black holes do not accrete very much. So what this figure is showing is a distribution of the accreted fraction. So basically how much of the gas or how much of the mass of the black hole is in gas versus its total mass. So 1 would be it's all gas, 0 would be it never accreted anything. And you can see that there's a giant peak here at 0. Most of these black holes that are in dwarf galaxies have not accreted very much at all. The largest one is about 13% or so. And so that's pretty interesting because that can actually give us a clue as to the original seed formation mechanism if these are seeds to massive black holes in the early universe. So if we can measure these black holes and be like, oh, if they're 10 to the 3 solar masses or 10 to the 5 solar masses or whatever, we can get a limit on what the seed formation mass is, and thus an estimate of what the seed formation mechanism could be, which is pretty cool. So these black holes do not accrete very much, but that doesn't mean that there are no dwarf AGN. And so I want to pivot now and talk a little bit about the Romulus simulations, which is a 25 megaparsec cubed volume of, what is it, certified organic free range locally grown supermassive black holes. Michael made this slide. But it's pretty cool. And so this Romulus has a much larger sample of dwarf galaxies with black holes. You can actually measure lots of them instead of the handful that I was looking at in the Zoom simulations. And so I'm going to present some results from that from a student who just finished, a doctor who just finished his PhD, Ray Sharma, who's working with Alison Brooks, as well as myself and Michael on some AGNs and Romulus. So I'm going to show the rest of this in a second, but it's a lot. So just look at this one plot. All right. So dwarf AGN in Romulus do exist, and what this is showing is the estimated X-ray luminosity. This is hard. There we go. This is all hard. Stick. All right. The X-ray luminosity estimated of these black holes versus the stellar mass, so 10 to the 8 to 10 to the 10. And so the colored points are the Romulus AGNs. They're colored by the Eddington fraction, so how much they're accreting. And then there are some observations that are in a legend that I've covered up, but these are at higher redshift and these are at lower redshift. And so you can see that they match the observations pretty well, but there's also a bunch of gray points which are not colored. And those are actually black holes which are undetected in Romulus. And by undetected, what do we mean? They have an X-ray luminosity. So what does that mean? Well, it means that they're undetected in that they are either their X-ray luminosity, while it exists, it is too close to or lower than the estimated X-ray background from the hot gas in the galaxy, and so you wouldn't be able to pick it out from the overall, like the AGN and the overall background are indistinguishable from each other, or they're just not accreting enough to be observed, like black holes down here you wouldn't really be able to see anyway. And so you can also see that in terms of the observable ones, if you look at the X-ray luminosity versus the star formation rate, and also star formation versus stellar mass, a lot of the AGN in dwarf galaxies in Romulus do match the scaling relations of the observations, but there's also a very large number of them that are not observable at all. And so in the Zoom simulations, none of the dwarfs are observable. In the Romulus simulations, some of them are observable, but a bunch of them are not. And to further go into that, these plots are all going to be the black hole mass versus stellar mass relation. And so this top one here, the colored points are colored by X-ray luminosity, so purple being faintish and orange being brightish. And again, the gray dots are the ones that you can't see because either the X-ray background is too bright or they're just not luminous enough. And then this one, they're colored by how bright basically how much over the background hot gas X-ray background threshold the luminosity needs to be. And so the tightest threshold would be the teal. Wait, the 5 is the. Yeah, if the luminosity has to be more than 5 times brighter than the gas, is that right? Then you would see them. Okay. And so you can see that depending on how much brighter the AGN needs to be over the background gas, you would see a different amount of black holes. Another thing that makes a big difference is whether or not the black hole is central or not. So there are wandering black holes in Romulus as well. And so if you put just the wandering black holes that are not central on a plot like this, you'll see that, first of all, they're not on the relation. And second of all, they're almost all gray. And so that's the detectability depends on the luminosity of the AGN, how high the X-ray background is, and whether or not the black hole is central. And overall, Ray finds that about 74% of central black holes and 88% of off-central black holes are hidden, either due to low luminosity or contamination from the X-ray background. So there's lots of black holes around, and we got to think of new ways to find them, like gravitational waves. So I am involved with the LISA mission, and LISA is going to launch in the mid-2030s and detect gravitational waves from merging black holes in this intermediate mass range. And so what this plot is showing is the LISA sensitivity function. So this is redshift here, and this is mass of black holes that are merging, the total mass of the two black holes. So if two black holes are at 10 to the 6, then their total mass would be 2 times 10 to the 6. These rainbow contours are the signal to noise that LISA will observe a merger with. So something that's very close by in this mass range, signal to noise 3000. But look, things that are from redshift 10 to 20 in this intermediate mass range of like 10 to the 4 to 10 to the 6, you can see or hear or detect with LISA. And that's amazing. That is really far away. There are not even photons from redshift 20. They cannot get to us, but gravitational waves can propagate through all media or none. And so we will be able to get gravitational wave information before, like from a time earlier in the universe than we can get light. Isn't that amazing? That's so amazing. Okay, that's amazing. Okay, so remember I said that there can be multiple black holes in dwarf galaxies. What if they merge? Sometimes they do in the Marvel and Justice League, mostly the Justice League simulations. So each black point I have on here is a merger that happens in a dwarf galaxy, and their mass ratios are written on here like 1 to 1, 1 to 5. So mostly they happen between redshifts of 0 to 12, and their mass ratios are about 0.2 to 1 or so. Something that my summer student did 2 summers ago, but this is now on archive, is that she used an analytic delay time calculation to figure out what the merger timescale will actually be, because in our simulations, when black holes merge, they get close together and they go bloop, and then they merged, which in the universe, there's a whole bunch of physics that we have just ignored. And so taking into account some dynamical friction, some gravitational wave hardening, some three-body scattering, she tried to figure out, will these actually merge in these dwarf galaxies? She found out that these 4 that are purple stars will. The pink one will take 30 gigayears to merge, and so they will merge, but it won't be observable by anyone like us. And the other galaxies were too poorly resolved for us to figure it out. So we think these mergers actually could happen and be detected by LISA. One other quick thing I want to mention is that if you don't talk about the dwarf galaxies, but instead also include the Milky Way galaxy in tallying up how many mergers there are, so including the massive galaxies in the Zoom simulations. This is not Romulus. We're back to the Zooms again. Sorry for the jumping around. So if you look at this distribution of mass ratios, you'll see a big peak right here, which is about a 1 to 50 if you zoom in on it. A 1 to 50 mass ratio is representative of an intermediate mass black hole from a dwarf galaxy merging with a Milky Way galaxy and its Milky Way black hole. So that's approximately what is going on there. So that's where this big peak comes from, is that these Milky Way black holes like to eat up the intermediate mass black holes. And that is what we think is going on in this situation that I showed in the very beginning of this HLX one. So what this probably is a dwarf galaxy or maybe a star cluster that has an intermediate mass black hole in it. It's been perturbed in its interaction with this more massive galaxy. The black hole is accreting, and eventually it will work its way into this larger disk galaxy and merge and contribute to this peak. And this is really important to think about if you are a numerical relativist, which I don't think anyone in here is, but if you are, this is a really hard mass ratio to model in terms of black hole mergers because it's super computational intensive, and so people avoid doing it, not because it isn't fun or cool, just because it's hard and takes a really long time. And so before LISA launches, we need to really get on this. So if anyone in this room is into that, we can talk. All right, so oh my gosh, I have 5 seconds left. Here are some conclusions. Summary. Many black holes in dwarfs aren't central because dwarfs merge with each other. And they can be really hard to detect whether they're central or wandering because their luminosities are pretty low. And there's a bunch of other X-rays going on in galaxies as well. Very few massive black hole mergers are in 1-to-1 mass ratios. 1-to-50 is pretty common, but LISA is going to be super awesome, and we love it, and we hope it launches on time, like everything else that launches on time. All right, thanks everybody.
All right, questions for Jillian. Who's back there? Oh, go ahead, Phil.
Hi, this is Phil Chang. Jillian, nice talk. Just a question. Why does the metals contribute to the formation of black hole seeds at all? Namely, why do too much metals kill off black hole seeds?
Good question. So metals enable cooling, basically. And so if you have a big cloud and it's able to cool, it will fragment and make a lot of small things. But if you aren't able to cool, it will instead make one big thing. It'll have a larger Jeans mass. And so you'll be able to collapse into a larger object. And so if you have metals, then you can cool and then you can fragment.
I see. So how big of these seeds are you talking about now?
The direct collapse seed model predicts somewhere between 10 to the 4 and 10 to the 6 solar masses.
I see. Okay.
Yeah, but there are other models that predict more like 10 to the 3 or 10 to the 2 with different mechanisms.
Thanks.
Urmila Chedemuri from the CFA. So you said somewhat casually that the 1-to-50 mass ratio mergers are things like HLXs. Can you please explain how you came to that conclusion? Because I'm always surrounded by people who tell me they don't know the origin of ULXs and HLXs. Like, what is your rationale?
So things like HLX1 will probably make the 1-to-50 mergers, but not all things like HLX1 are intermediate mass black holes. So there are a lot of, so a ULX is an ultra luminous X-ray source. The H stands for hyper because it's more than ultra. So it's hyper. I don't know what happens if you get brighter than that. Mega luminous? I don't know. Anyway, so a lot of ultra luminous X-ray sources are smaller black holes that are either doing super Eddington accretion or they're being beamed. And so not every ultraluminous X-ray source is an intermediate mass black hole. And so and how many of them are one or the other is a vigorous debate, which you've perhaps witnessed. And some people think there are no intermediate mass black holes and all ULXs are beamed, emission from stellar black holes. And some people think the opposite, and they can fight over it. But I think some of them are intermediate mass black holes, and many, but probably most of them aren't.
Shen. Very exciting results. You mentioned that because the profile of the dwarf galaxy are cold, that's why it gets in very slowly. So if it's actually a cusp profile, was it getting in reasonable amount of time, or black hole going to the center? I mean.
So we don't have any cuspy dwarfs in our work, but other work by Thomas Tumfall, who's one of Lucia Meyer's students, has shown this, that if you have a cuspy dwarf, they the black holes do merge much more quickly, and a core dwarf they don't. And so yes.
Okay, so then can this be like an indication of whether dwarf galaxy has cuspy or chord profile, like an additional constraint of how much of wandering black holes we are seeing?
I think it's a lot easier to measure the density profile than to measure the wandering black holes. But in theory, yes.
Yeah. Of course. Thank you.
Aren't there any on Zoom? Okay, Andrew.
Hello, Sandra Thompson. No, it's a completely different thing. This is really interesting. I was wondering about the timescale thing you were talking about. You said there was a student who calculated with you the timescale to merger. I think you were saying after it's actually merged in the simulation, but like the unresolved phase. Is that?
Yeah, we take the moment right before they merge, and we say, okay, what? And then there's it takes into account the density of the stars and some.
Right. So should we worry? I mean, that because if the simulation is then treating it as one big merged black hole, but actually it's going to take 30 gig years to merge. If there's a ton of these, should we be worrying that we're getting this wrong?
Well, it's not a ton of them. 80% of them, 4 versus 1, apparently merge in a reasonable amount of time. No, this definitely needs to be expanded to something like Romulus, which is something that Michael and I have talked about, but we have not had the human power to do. But something with actual more robust statistics would be a really good idea, because for them, for most of these, it does seem like they merge pretty quickly. And in dwarfs, it was that was the big question, is that they could just slosh around forever and never find each other. And so is that happening or not? And it appears that at least some of the time they're finding each other. And so, but this does take them at their closest point right before merger. And so if there are dwarfs that have black holes that don't find each other, that obviously isn't included here, because then they definitely don't find each other. So there's some with multiple black holes that don't merge at all as well.
Okay, and with that, we should thank you.
Thank you, everyone.
Next up is Casper.
And I work at NYU Abu Dhabi as research fellow, doing my postdoc. And I've been working in recent years on kicking black holes, which is essentially just studying the influence recoiling supermassive black holes have on galaxy evolution. And well, first we heard about gravitational waves. So I won't go very much into details, but essentially what happens is two heavy objects orbiting each other, so undergoing like feeling acceleration, they tend to emit gravitational waves, and they essentially propagate at the speed of light. But what is really cool, what happens is if the two massive objects like black holes have different masses or spins, we have a net momentum flux of gravitational waves. So we lose linear momentum in one direction more than in the other direction. And as we know, linear momentum is conserved. So the resultant mergent actually gets ejected with quite high velocities. And you can see plots on the right presenting different models. Then those velocities can reach like 1,000 kilometers per second for aligned spins. And if we have unaligned spins, it can be even like up to 5,000 kilometers per second. But why should we study gravitational recoil rather than gravitational waves? We all heard about gravitational waves, Nobel Prize, big things. Because gravitational recoil actually is visible in galaxies, and gravitational waves do not impact galaxy evolution as much. So we can high speeds, 1,000 kilometers per second, like order of escape velocities from galaxies, because those are heavy objects. They carry lots of energy with them, and they can potentially influence galaxy formation. So we can have offset quasars. So on the plot on the right, you have one candidate for recoiling black hole. It was later proven not to be recoiling black hole, but you have bulge of the galaxy and AGN that is offset from the center. And because it's offset from the center, we have offset AGN feedback, which means that we heat up gas somewhere further away from the center. So it's not as localized. And therefore, we can quench star formation at different places at the center of the galaxy. And also it's observable, so we can test our predictions from simulations on observations. Pretty cool. I work in NIHAO project, which is numerical investigation of 100 astrophysical objects. It's a set of zoom-in simulations. It has million particles per halo. We have halo masses at redshift 0 between 10 to the 9 to 10 to the 14 solar masses. And yeah, there's large sample size. Around 30 of those galaxies have black holes of interest. And cool thing is, what is not done usually is because those galaxies can merge, we have realistic morphology of galaxies at the time of merge of black holes, which means that we don't have ideally spherical potential, which is very often found in studying of recoiling black holes. And right, we have important physics. So before I worked in the group, we had black hole formation, accretion, and feedback. We had cooling, we had metal formation, stellar feedback, and supernova feedback. There was one part missing to track recoiling black holes, and it was dynamical friction, which was Michael's prescription that was recently added. And with that code, we are able to get black hole stereo-mass relation and a couple other important relations pretty well. As you can see, the blue points are our simulations, the pink line are observations, which is pretty nice. Right, what I did, I changed the velocity of central black hole because we don't have this sub-grid resolution to actually see the mergers. So I looked when the mergers happen, and I assumed they happen kind of instantaneously. Of course, there's less parsec problem. There's hard time of it's really hard to merge the black holes, but I assume they merge. I ran the simulations 1 gigayear after the event, and I looked at the data. So let's go to findings, which is something interesting. I will talk about 5 major points, which will be oscillations, accretion, profile, scaling, and symmetries. Let's start with oscillations. Here I have plots, and those are plots where I kicked with black holes with 90% of escape velocity. It's in quotation mark because it was adopted from Chomsky. It's not real escape velocity from galaxy. It's something different, but scalable with escape velocity from the galaxy. And the cool thing is, the interesting thing is they do not decay within 1 gigayear, at least in our simulations. But if you compare, if you compare the in-plane cake, which is the blue line, and normal to the plane of the galaxy, you see that in the galaxy, it's kind of damped because we moved through the denser medium, which is kind of what we expect. But not all of them look nice, so some of them don't oscillate. Some of them oscillate only in the plane of the galaxy, but so the trajectories are very, very sensitive to the the magnitude of the cake. So, and another important feature of this plot is the accretion rate, because it also converts to brightness, and you can see those spikes of accretion, which could mean that the black hole would be visible only when passing through the center. And yeah, I also simulated it for a bit longer to see if maybe it would decay for longer if we simulate it for longer, but not really. Yeah, let's move into accretion to see if something actually happens. And you saw those spikes, but it so happens that with Bondi oil accretion, those spikes are insignificant. So the green line is our stationary counterpart. The rest of the lines are moving black holes. So, well, they do not move. And it's because in Bondi oil accretion, in denominator, we have velocity, which means that moving black holes essentially do not accrete much. But there's a small asterisk. If we change the model of accretion mode, some interesting things can happen. So Bondi oil, as I said, if we kick, nothing interesting happens. But for example, with alpha disk model, if we kick black hole from the center and then it comes back, it can grow even more than its stationary counterpart, which is really interesting. So depending on which mode accretion that would be correct for wandering black holes, which is still under debate, it behaves differently. So we can regulate growth of the black hole this way. Right. Let's look at profiles, which is another cool thing. If you look at two left galaxies, which are lower massive galaxies, you see that the lines are kind of mixed up, so boring. Those are gas density ratio compared to when the kick occurred and like after 1 gigayear. But there is something interesting happening at the plot on the right. So let's take a look at it. Well, as I said, we have reference values. And we have this huge well of low density gas. If the black hole is stationary, if they are kicked, well, essentially, it's very similar to the case if we don't put black hole into simulation at all. Yeah, and what we think is happening is we have small black hole, it doesn't radiate much energy, but we have big black hole, it tends to hit gas around it, which means it tends to push gas away. Right? And recoil can also influence star formation rates. So as you can see, plot on the right, if the black hole is stationary, it quenches star formation. But if it's kicked, it can not quench because the black hole doesn't grow, so we don't have as much AGN feedback. And for more massive galaxies, the phenomenon is even more complex, and the effect can be slightly weird. So for this galaxy, actually the highest star formation rate is actually whether it's kicked or not kicked, it's because exactly the same as the black hole was stationary. So yeah, it's hard to predict in general. Right, scaling. I don't have my time, so I just brief quickly. That's the escape velocity that we use. It's dependent on the mass of the halo at the time of the kick and the redshift. And if we plot our data on that relation, it kind of seems to resemble the one quite nicely. There is like tens of percent, so not that big. Right, and symmetries. Those plots are really nice, but essentially what I was expecting was that if I kick black hole in one direction versus another direction, I should have similar escape velocities. But if I kick them with 80% of escape velocity, we have two very different trajectories. And I thought that maybe black hole was moving initially, but it was not. If I don't into the kick, it stays in the center. So it seems like there could be effects of local environment on trajectories. And as I said, the galaxies tend to merge. With galaxies merge, then when black holes merger occur as well. So the morphology is highly not symmetrical. So again, hard to generalize any big, like it's hard to generalize findings because the local environment matters so much. Right? That would be it. And to summarize, if we kicked it with 90% of escape velocity, the black holes would oscillate for over 2.5 gigayears. And stationary black holes accrete much more if we think about Bondi oil accretion. Recoil does not impact low mass galaxies as much. It hinders growth of black holes, but they're able to pick it up later on. And of course, low mass galaxies, low AGN feedback, so much change. In bigger, more massive galaxies, recoiling black holes can influence star formation rate, and escape velocity, how long the normal to the plane of the disk resemble Tox's relation, which is nice. And trajectories depend strongly on direction of kick and velocity. Thank you for your attention, and I would be happy to take any questions. And there's my email if someone to.
Questions for Casper? Okay, Phil, I saw your hand first.
All right. So I have one quick question. So you mentioned that if you have a moving black hole, alpha disk prescription for accretion basically allows to accrete more. How does the alpha disk prescription work basically for moving objects in your simulations?
Well, so essentially the alpha disk accretion we use doesn't include any moving part. Like there is no moving factor in the alpha disk. We just assume it works just as if it was stationary, which may be not perfect, but that's what we use.
Go ahead, Michael.
Yeah, Michael Tremmel asking, can you go back to the slide where you had the different directions? I just want to make sure. So you're saying that when you have a kick out of the plane of the disk, it actually doesn't go to as large of a distance? Is that,
So,
I mean that right?
This is both are out of plane. It's just one is in.
Oh, I see.
One is aligned with angular momentum. One is anti-aligned.
Okay.
So if everything was nice and you would have symmetry, we would expect them to be similar, but they are not similar.
Right.
And they start differing very closely. So I assume it's effect of the local environment in the center.
That makes sense. Can I ask a quick technical question? What's the mass resolution of the simulations you're doing these kicks, and what's the mass of the black holes?
So the mass of the black holes, let me give you the correct numbers. So for this one, the halo mass would be, wait. For this one, the mass of the halo is 7 times 10 to the 12. And the mass of the black hole is 8 to the 8.
Okay. Cool. Thanks.
Go
Hi, this is Alex Liu. I wanted to ask, well, so for this object, let's say where you have like two very different trajectories of the black holes, for like the scheme where the black holes like for the blue curve, let's say, do you know if in that case is the black hole gravitationally unbound from the galaxy, or is it just following like a much wider orbit around like the center?
I didn't check that exactly. So I didn't run this simulation for long enough. And it's still within viral radii, so I would assume it still have time to come back.
Okay, thank you.
Okay, then let's take Casper one more time. And next up, we'll hear from Nicole Sanchez.
All right. Hello. Thank you so much for having me. And thank you to Allison for organizing this awesome conference. It's amazing to be in the same room as. So I'm going to be talking about the third and final chapter of my thesis here, which I just successfully defended last month. And so I'm going to be relating supermassive black hole feedback to the metal content of the CGM and how we can learn something about this metal content through where the supermassive black hole lies on the M sigma relation. And thankfully, I really appreciate where the SOC put me during the day because you've already been primed. You know all about the CGM, thanks to Urmila's talk earlier. So I'm interested in exploring the effect of the supermassive black hole on the CGM. And so if I'm thinking about galaxies that we're going to see the effect of the supermassive black hole, my focus has been on L-star or Milky Way mass galaxies because they live at this knee of the M-star-M halo relationship here on the right. And so this knee is where galaxies transition from being dominated by stellar processes to being dominated at higher masses by supermassive black hole feedback processes. And more recently, in the last 10 years, since the installation of the cosmic origin spectrograph on HST, we've started exploring the impact of feedback processes such as supernova and AGN feedback on gas in the CGM. And since those observations have started, simulations are working hard to see if we can match those observations. We've talked a little bit about those today. And so if you were at NBSE last year, I very thoroughly convinced you of the results of the second chapter of my thesis, which was describing the impact of supermassive black hole feedback enriching the CGM in a few simulations. And I did so by comparing to some observations from the COS Halo survey, which looked at 39 L-star galaxies in the local area using background quasar spectroscopy. And specifically, I compared two column densities of 0.6 as a function of radius, which you can see here on the right from Tomlinson et al. 2011. And so column densities of 0.6, you can think of as a proxy for the hot gas in the halo. And these results were not reproduced until 2018, 2019, including within my paper. And so I'm not going to try and convince you of the results of my paper. I'm just going to tell you that using 4 Milky Way mass galaxies with black holes that were run with Chang'e and had similar, used the same physics and a similar resolution to Romulus 25, which you've heard all about today, as well as rerunning those simulations without black hole physics. I calculated the column densities of 0.6 for these 8 galaxies and found a discrepancy in the amount of 0.6 that was in the CGM, where galaxies with without black hole physics had almost an order of magnitude less 0.6 in their CGM. And basically the key result of this paper was that the supermassive black hole is enriching the CGM by ejecting metals out from the center of the galaxy where they're being formed and propagating them out into the CGM. And so my work now has been asking the follow-up question, if we know that the supermassive black hole is ejecting and evacuating these metals from the disk, where are those metals going? Are they going to the CGM? Are they being evacuated out into the IGM? Are they returning back to the disk? And so to answer this question, I'm using everybody's favorite 25 megaparsec volume, Romulus 25. Some reminders, we've heard a lot about these simulations today. So I've got the resolution, the force softening length, and some of the observational constraints that it's been optimized to match. But in particular, I've selected 140 galaxies between 3 times 10 to the 9 and 3 times 10 to the 11 solar masses. So L star Milky Way mass and a little bit below. And then divided the sample into both star forming and passive or quenched galaxies using a specific star formation rate cut at redshift of 0, which I should have included there. So here they are. This is the M sigma relationship for these 140 galaxies. I've also included the 4 galaxies that I mentioned earlier as well, just for comparison. And in addition to having divided the sample into the star-forming galaxies in the squares and the quenched galaxies in the circles, I'm also using the empirical relationship, this gray line here for M sigma from the Cormandy and Ho 2013 paper, to define a population of overmassive galaxies, that is, galaxies that have supermassive black holes that have accreted more than the empirical relation of Cormandy and Ho, or on the other side, galaxies that contain black holes that are undermassive compared to this relation. And so I've used this definition here as my x-axis. So you have galaxies that have overmassive black holes on the left of this line and galaxies with undermassive black holes on the right. And my y-axis here is what I'm going to call the metal retention of the disk. And so this is the amount of metals present in that galaxy's disk or central region for the quenched galaxies, divided by the total metals produced by that galaxy. So, you know, a galaxy along this 0.6 has retained 60% of the metals that it has produced during its life. And there's this interesting relation that you can see in both the star-forming galaxies and the quenched galaxies, where overmassive, supermassive black holes, so the galaxies that contain these overmassive black holes, lose a higher fraction of metals out of the disk compared to galaxies that have undermassive black holes. And in addition, if you look at the color scale that I've used, so this is the fraction of total disk metals in stars. So what fraction that is retained, what phase is it in? And so in the galaxies with undermassive black holes, most of the metals that are still in the disk or the central region are locked in stars, whereas galaxies with overmassive black holes, these metals are still in the gas phase. And most metals, at least in our star-forming galaxy, are being maintained within the halo of the galaxy. And so let me explain that a little more clearly. So the y-axis of the previous plot is this x-axis here, our disk metal retention. And along the y-axis is the metal retention of the CGM. So the way to read this plot is, if we look at this, our friend, this orange galaxy here, it has 40% of the metals that it's formed stored in its disk, 20% are in the CGM, and 40%, the remaining 40%, have been lost to the IGM. So galaxies that fall along this line, say, if I can point precisely, that orange friend, it's got 80% of the metals in its disk, 20% are in its CGM. And so all of the galaxies that lie along the gray line have all of those metals maintained within the halo. And so any that fall below that line have lost metals to the IGM. And so at least for the star-forming galaxies, right, our squares, most of the metals are still maintained in the halo that are formed, right? We're not evacuating a lot of these metals out into the IGM. There's a little bit more of that is happening in our quenched galaxies. About half of them are losing more metals to the IGM. But there's an interesting, spoiler alert. So there's this interesting trend where the galaxies that are retaining most of their metals are maintaining those in the disk. And again, those are being stored in stars, whereas the galaxies that are losing metals out to the CGM are maintaining their disk fractions in the gas phase. And so, as I briefly showed, this also trends with this deviation from M sigma, this over or under massive quantity of the black hole. And so the galaxies that are maintaining the most metals, and most of those in their disk and locked in stars, are also the ones that that contain a central undermassive supermassive black hole, whereas the opposite is true for the overmassive black holes. And so we can learn a little bit more about this when we think about the evolution of these galaxies through time. So here I have the star formation history as a function of time and the cumulative accreted black hole mass. And in the overmassive black hole case, these galaxies that end up with overmassive black holes have earlier star formation and earlier black hole growth, which leads us to this conclusion that we sort of have these two evolutionary pathways, where in the case where the galaxies grow earlier and their stars are forming earlier and their black hole is growing earlier, you have two effects. The black hole is ejecting more metals from the disk out into the CGM, but not necessarily out into the IGM. And there's more stellar regulation, and you're seeing more of those disk metals being retained in the gas phase. And then the opposite is true in the undermassive black hole case, where more metals are being retained in the disk and there's less stellar regulation, so those disk metals end up being locked in stars. And this is consistent with some of the results from Ray Sharma's work in 2020, where he found that galaxies with undermassive black holes, though small caveat, we defined our over and undermassive black hole slightly differently, but galaxies with undermassive black hole, Sharma et al. 2020 found evolve like galaxies without black holes, which is very similar to what I found in my paper in 2019 as well. And so this is the gas phase metallicity gradient, so the median for the overmassive population and the undermassive black hole population. And you find in the case with the undermassive black holes in blue, you get this buildup of metals in the center. And remember, this the disks or the galaxies with undermassive black holes are also the ones that are have most of their metals locked in stars, and yet they still have in the gas phase this buildup of metals compared to the sort of flatter profile that you see in the galaxies with overmassive black holes. And so what we find is that the scatter in M sigma appears to indicate how effective a supermassive black hole might be in ejecting metals from its disk, which is pretty cool. And I think it's great that we continue to kind of tie the physics of black holes to the motions of the metals in the galaxy. But you might ask the question, well, can we observe this? And the answer to that question is yes, but not quite yet. So we really need new upcoming surveys to do this that are pairing observations of the CGM, such as the UV quasar spectroscopic surveys with COST, to dynamical measurements of black holes within the galaxies inside of those CGM. And so this is one prediction of the column densities of C4 that we might be able to see once surveys like COST holds, which is in the process of doing these observations now. We might be able to determine whether we can see this trend then. So with that, I'm going to leave up my slides. Thank you so much for your attention, and I will now take questions.
Questions for Nicole. I had no idea cost holes was a thing.
Oh yeah, it's happening. Dynamical measurements, pairing them with UV observations, it's gonna be lit. Wow, did I explain it so well that nobody has any questions?
It looks like Tom has a question. Oh, and so do some other people. Urmila, why don't you go ahead?
Urmila Chedai-Murray from the CFA. You did explain it very well. But so I'm trying to figure out the arrow of causality here. Like, are the is more material ejected into the CGM because the black holes are overmassive and were, presumably they were overmassive because they were feeding a lot. And, most of our prescriptions for these simulations say that the feedback efficiency is proportional to the accretion rate. And so, is that just what's happening? Is it like it ate a lot, so it burped a lot, and then you have then you end up with a lot of metals in the CGM? Or is the arrow of causality going the opposite direction? Or is it just like kind of a cycle? And what you're telling us is basically like if you measure one thing, like deviation from the M sigma relation, then that is bonus also telling you about how metal enriched the CGM is.
So the first and the third thing. So yeah, right. Like it's because our prescription is that the feedback is directly proportional to the accretion, right? The overmassive black holes are growing more, so they are more energetic, so they are ejecting more material. There's also, I think, the kind of key thing about the M sigma relationship is also the ratio between the stellar dispersion, which is a proxy for the potential, right? And so I think that having more massive black holes in lower potentials is also kind of giving the black hole it's like the big kid at the playground, right? It's got a bit more of an impact in that way. And so I think, does that answer your question? Okay, great. I think there was a second part, but I got lost.
Okay, maybe one more quick question. Tom, did you want to go ahead?
Okay. Tom Quinn. Could you comment on how this work relates to Andrea Riccardi's work on how black holes, the black hole stellar mass relationship tends to trend toward the existing relationship? Particularly when you say it seems the way you've laid this particular slide, if overmassive black holes regulates star formation, and you would think there would be a trend away from the black hole mass stellar mass relation. Or maybe I'm just misunderstanding. Yeah, it's quite likely.
Sorry, can you just say that one more time?
Sorry, just to keep us on time.
Oh,
maybe it's too long. Okay.
Maybe if this is going to take a minute, I might actually ask Michael to come up. I'm sorry to cut you guys off.
Right.
It's good. Let's think about this and get back to it. All right.
We'll
Thank you again, Nicole.
Oh, I hope I'm using the right color thing. All right. Yeah, thanks. I'm Michael Tremmel, and I'm going to talk about more black holes. Oh, I'm gonna take my mask off here. In particular, I'm going to talk about some new simulations I've been working on, high-resolution simulations of dwarf galaxy mergers. And I just want to mention that the simulations I'll talk about right now are kind of a part of a larger effort to run higher resolution simulations and kind of bring our black hole models into the next generation of high resolution simulations with updated feedback like Ben's super bubbles that he mentioned in his talk. So yeah, keep that in mind. This is just one part of that whole. So I'm just going to get right to the motivation. And I'm really lucky, again, kind of like Nicole, that I had all these talks that introduced the work beforehand. So the main motivation for this work is gravitational waves. So they're going to open up a whole new way of detecting black holes. Right now, the pulsar timing arrays are kind of on the cusp of detecting the first supermassive black hole mergers. LISA, the laser interferometer space antenna, will be able to detect black holes at high redshift at lower masses, like Jillian described. And this is really cool. And in particular, LISA's great, and this is, again, another plot that Jillian already showed, that because it will be able to see so far back in time and will be able to see small black holes. And in fact, the kind of bread and butter of LISA is going to be these low mass black hole mergers that result from low mass galaxy mergers at high redshift. This is going to be the majority of the LISA data stream, and it's going to be what tells us the most about black holes at high redshift, which is really exciting. And then if you combine that with new electromagnetic observatories like next generation X-ray telescopes and JWST, we'll really enter into a new era of what people call multi-messenger astrophysics, where we can combine gravitational wave data with electromagnetic data to learn more about how black holes grow as a population over cosmic time. Because we're really learning about brand new populations of black holes that, again, as Jillian mentioned, would often be invisible to us otherwise. Now, what do we need from simulations to actually improve and understand these, improve our understanding of these systems further? The first thing is that we need to actually have simulations that model black holes in low mass galaxies, that see them in early times so that we actually have the black holes at high redshift when these mergers are taking place. Again, Lisa's bread and butter is going to be redshift greater than 2 and really like redshift 3, 4, 5 for mergers. So having black holes exist in the early universe and be within resolved low mass galaxies. We have observations that tell us that black holes exist in these galaxies at present day, and yet they're often ignored in cosmological simulations, especially large-scale cosmological simulations. The next thing, maybe more obvious, is that we need realistic black hole dynamics. Black holes so that we can predict when and where these black holes will meet each other in the center of their galaxies after a galaxy merger, to predict when and where binaries will form and eventually merge. So again, as people have nicely already talked about, the Romulus simulations were a nice step to do both of these things within a large-scale cosmological simulation. So together, Romulus 25, Romulus C, and I should really get better at mentioning Romulus G1 and G2. Together, those simulations have thousands of galaxies in a variety of different environments. And we took work to ensure that, one, these simulations have the resolution to resolve dwarf galaxies. They form black holes at early times. They form black holes in low mass galaxies, and they allow them to exist within low mass galaxies throughout cosmic time. And they dynamically evolve in a realistic way so that we can track their dynamics to sub-kiloparsec timescales. So when looking at Romulus, we've done already some really nice things. In my paper a few years ago, we looked at the population of mergers overall in Romulus, and we found that the dynamical evolution of black holes varied dramatically. You had some mergers like this one I'm showing here, where the black holes found each other relatively quickly and formed a binary pretty quickly following the galaxy merger. But we also found systems like this, where you have a wandering black hole for gigayears within the same galaxy that finally eventually makes it to the center and forms a binary. And so the overall distribution of formation times to binaries, this galactic scale evolution can vary a lot. And it comes down to a lot of the properties of the merging galaxies themselves. So in this top case, the secondary black hole has a galaxy around it, while in the bottom case, the galaxy no longer exists. It's been entirely disrupted, and the black hole has been left on its own, making the black hole have really long timescales to reach the center. So it's really the cores of galaxies that are bringing black holes together in these simulations. And we were able to use this information from Romulus to make predictions directly relevant to Lisa. So we can take this kiloparsec scale delay time that we predict from Romulus of this additional evolutionary stage. We can apply it to these semi-analytic models that people run to predict Lisa observations. And we find, if just looking at the blue line here, that compared to these other models that don't include this extra delay, this decreases the amount of mergers we predict Lisa to detect by a factor of a few. It also changes the redshift of distribution of those mergers. So we've already learned something interesting about when and where mergers take place. The problem and the weakness of all large volume simulations like Romulus is resolution. So I mentioned that the bread and butter of Lisa is dwarf galaxy mergers. This is what a dwarf galaxy merger looks like in Romulus. And I want to remind you, Romulus has the highest resolution of simulations of its class. So this is as best as we can do. So you look at TNG 50, look at the Eagle simulation at highest resolution. This is what a dwarf galaxy merger looks like at redshift 4.5, which we're trying to use to understand Lisa results. So what we can do is, like we like to do in this group a lot, focus our computational power just on these systems rather than the whole volume of thousands of galaxies, and we can get much better resolution and begin to actually do more work looking at the environment and the evolution of these black holes in merging dwarf galaxies. And of course, as you go to higher resolution, you get better physics, which is what we're trying to do. And so that's what we did. We took a galaxy merger selected from Romulus 25, and we reran it at much higher resolution, putting the black holes by hand in the two progenitor galaxies at redshift 12, starting at 10 to the 5 solar masses. And we ran them with time. I mean, watch the little movie here. The black holes are white dots, and the stars are shown as blue and reddish dots, and there's hot and cold gas. The black holes eventually merge.
but you see there's some wandering that goes on for a few 100 million years. And the galaxy throughout this whole process is also changing dramatically over time. So we can make predictions for when the black holes merge, as well as what their environment looks like beyond that merger. And we can see where's the binary evolving in the first place. So because, like I said, this is part of a larger effort to update our physics model, the first thing to test is how do variations in your model affect your results. So what I'm showing here is the mass evolution of the two black holes. In solid lines, we have the mass of the primary black hole in the more massive galaxy, and the dashed lines show the mass evolution of the secondary black hole for 3 different models. The blue being our fiducial model, we have what is the typical accretion rate prescription, a Bondi accretion rate boosted by a certain factor for high density gas. That's more or less what we did in the Romulus simulations. In green, we have an addition of angular momentum limited accretion. So what we do is we attempt to estimate the rotational support of gas around the black hole and decrease the accretion rate, accounting for that rotational support. This is also something we do in Romulus. And then finally, in this orange one, we have a version where we've dialed down the black hole feedback by a factor of 5. Again, that efficiency is how much energy is the black hole inputting into its environment. And so just from these 3 models, we can learn some interesting things already. The first one is that this green model, this angular momentum limited accretion, has no black hole growth in it whatsoever. And this is not something that we saw in Romulus. But what we get is when you go to high resolution, there's a ton of angular momentum on very small scales. And if you try to account for it in this very simple way that we do, you just shut down accretion entirely. So probably in reality, there's much more complex instabilities that are taking place to sap away angular momentum. The other thing that we can see is the effect of decreasing the black hole feedback. In this case, the majority of the effect is on the secondary black hole. The primary galaxy's black hole, the solid line, doesn't change very much in these simulations. It's not regulated by its own feedback. In the lower mass galaxy, however, decreasing feedback means the black hole grows by a lot more. So that means that in the primary galaxy, growth is limited not by black hole feedback, but actually by supernova feedback. So if we run that same simulation again, but dial down the supernova feedback, we get runaway black hole growth. So the supernova are limiting the gas available for the black hole. It's not the black hole feedback in the primary galaxy. In the smaller galaxy, there's not enough stars for that to happen, and the black hole really has to regulate itself. The other thing we can look at is the dynamical evolution of the black holes. And they actually do merge at different times in these simulations by a few 100 million years. And again, we find is that it all has to do with the properties of the secondary galaxy when the merger starts. So if we look at the green case here, the one where the black holes don't grow much at all, the secondary galaxy looks like this. There's a nice dense core of stars at the center, and the black holes nicely at the center of that distribution. If we look at the orange case, the galaxy is a little messier. It's a little bit awkward to find the exact center in terms of the stars, but the black hole's more or less in the middle of the denser population of stars. And then finally, the blue case, the dwarf galaxy is a train wreck. The additional black hole feedback in this blue case has allowed the galaxy to be disrupted by a recent merger, and the black hole actually isn't even in the center of the galaxy anymore. It's well off center. And so this is why the black holes take different times. And just as before, when you have the black holes existing in 2 separate galaxies, like happens in these 2 cases, you get a much quicker merger, while in the blue case, that galaxy gets disrupted. The black hole is over there in that little disrupted tail, and it takes a bit longer to reach the center black hole in that case. And in this case, the black hole feedback and growth model is the thing that's affecting that galaxy and influencing its own dynamical evolution. And finally, what we can look at is, like I mentioned, the environment that the black holes are evolving within. So what does the galaxy look like? Or in this case, what does the dark matter look like? So we can follow the evolution of the dark matter profile as a function of time with a primary halo throughout the simulation. This gamma parameter that I'm plotting as a function of time here essentially looks at the central slope of dark matter. A gamma of 1 is an NFW profile, a cuspy profile, and a gamma of 0 is a flat chord profile. And what we see is that after the merger event takes place, the dark matter profile of the galaxy becomes more or less chord. And that takes place whether or not you have black hole growth or not. Even in a simulation with no black holes, this always occurs. And so the black holes are evolving in a core dark matter halo after they merge, after the merger is done. And that can affect what happens on smaller scales. So if we think about how do the binary black holes evolve further through time, as Jillian pointed out, core dark matter can make a big difference. So just to, I guess I'm at 0 now. I didn't notice that. Variations of black hole growth models affect and have consequences for what we predict about LISA sources. High redshift mergers have core dark matter profiles. And the next steps in this is using Andrew's awesome genetic modification code that he talked about a couple of days ago or yesterday, I don't even know, to change the properties of these mergers to see how does the galaxy properties affect the merger dynamics in more interesting ways. So thanks for your time. I'll take questions.
Okay. Do we have any questions for Michael? Oh, I see a hand over there. Is it Bra? Yeah. Pop.
This is Farah. I'm really interested in the core dark matter profile, as you might expect. Can you go back to that plot? So it seems like the core dark matter profile is persisting for a giga-year afterwards. Do you know how long it can persist due to that merger?
Yeah, we only run the simulation to redshifts 2.5 or so. So that's when the galaxy was selected. So we can't really run it much beyond that.
Okay.
We'll start running out of zoom region. Does that make sense?
Do you have any feeling of whether it would persist or become erased?
You probably be better to answer that question than me. I'm not sure. The star formation is pretty consistent over time, so I'm really not positive.
Okay, thank you.
Yeah.
I'm gonna cut us off there and actually switch over to the flash talks because we're running a couple minutes late. Thank you again, Michael. Yeah, so our final 15 minutes of the day is in flash talks. Most of these will be in person, but and I apologize. I am going to butcher your name if I try to say it. Introduce yourself when you get up here.
Okay, I'm going to take this off. That's what we do. There it is. Okay, great. Okay, good afternoon. My name is Parag Odes. I'm a student of James Wadsley's, and I've been working on implementing molecular hydrogen cooling into gasoline under our new radiative transfer protocol. So one of the first studies that we did with radiative transfer in gasoline was Benincasa et al. This was about 2020. And they ran isolated disk galaxies with superbubble feedback and heating by FUV. And what they found is when they had these two feedback mechanisms active, they got these nice clumpy regions of high density gas in their galaxies. And if we compare these to observed galaxies, such as this one from the Things survey, I think this is actually going to be one of the flagship galaxies on Bespoke. We find, at least comparing by eye, that these two profiles are very similar. For instance, in the neutral hydrogen profile of this Bespoke galaxy, we have all of these holes in the neutral hydrogen, which is a bit surprising at first until we realize that a lot of those holes correspond to high density clumps in the molecular gas tracer of Cl. And we see that we can sort of resolve similar things in our simulation. But the thing is, this isn't actually a model of molecular gas, since we didn't have H2 in gasoline at that time. This is just a proxy. So this is just a density cut saying all gas above a certain density will classify as molecules. Since we know that we can get this clumpy structure, we'd like to actually implement H2 cooling into gasoline itself. Now, we know that H2 cooling is necessary to form molecular clouds. It has an additional benefit of actually boosting cooling in the region of about 10 Kelvin to 10,000 Kelvin. This is a plot from Nedin and Krastov's model, where the blue shows the full cooling model with H2, and the red is without H2. And we can see the little boosting down here for various metallicity. Now, the difficulty we have here is that modeling H2 requires non-equilibrium chemistry. So it all depends on if you have like a cloud of ionized hydrogen and it cools rapidly, faster than it can recombine, then you'll have an excess electron fraction, which enables H2 to form by this gas process. This is all fine. Gasoline can handle non-equilibrium chemistry, so we just need to plug these rates in here, where we just consider the formation processes for H2 and the dissociation. It seems straightforward, but there's an issue, and that's we're running into issues with our restart program because the fractional abundances of H2 don't just depend on the temperature and density now, but the temperature and density that it was before the gas cooled because of all this non-equilibrium electron fractions. So that's where we're at right now, and I'm out of time. But if you guys have any ideas or any questions about this, feel free to let me know. That's just where we are at the moment.
Phil? Phil Chang is next.
Works. Does this thing work? What does this thing do? I don't know what these things do. One. All right. Oh, wait, what's that? Holy crap. Go back. All right. So, all right, I'll talk a little about moving mesh hydrodynamics in Chang'e. All right. So, I've been developing the moving mesh module in Chang'e for quite a few years now. I think I started in 2016 and been doing it ever since. So, this is a list of my collaborators. A few of these names you recognize: Tom Quinn, James Bradley, right? And then the people highlighted in red are basically people at UW that work with me: Logan Prost, Alexandra Spalding, Sinead Humphrey, Benai Balson, Sarah Benoit Bros. They're all here basically today, either in person or virtually. And then some other people I've worked with more recently include Zach Etienne. Oh, this should be changed. He just moved to the University of Idaho. Shane Davis and Jan Peijian, who's actually a Flatiron fan. Okay, so anyway, let me talk a little about Manga. So Manga is just a moving mesh solver that's sitting on top of Chang'e, right? So basically the same thing as Chang'e as before, right? And it has a few things. It basically has hydrodynamics. That's basically upper left, okay? It has also self-gravity because it builds upon Chang'e's thing, and also has basically different equation of states, right? So in particular, if you look at this last bottom plot, if you look at the star is about 10 to 6 centimeters. So that's a neutron star. This is actually a nuclear equation state, actually from stellarcops.org, right? For those of you eagle eye, or not even that eagle eye, you might notice that the SPH simulation and the moving mesh simulation at the top are slightly off, right? The reason why they're slightly off is that the moving mesh simulation, this one is wrong, okay? This is, I thank Tom for this, right? Because when I first built this thing, all right, I assumed the time steps were done like in the right order. And this actually literally took me, I think, a year to figure out that basically something was being called twice in the SPH version and not in the moving mesh version. And the only reason why I called it was that I noticed that there was a print statement that was just once in one thing and not in the other. Thanks, Tom. All right. Anyway, that's okay. That's okay. That's life. So the other thing I want to point out is that we also have some other physics that we put in more recently. So this is work that's been done. I did with Shane Davis and Jan Peijian. This is radiation, right? And this is solving the time-dependent radiation transfer problem in the reduced speed of light approximation. So basically, think of it is that this is radiation with no approximations, except for the number of angles you want to do, right? And so this is actually pretty hard to do if you do it normally radiation, because what happens is that normally when people do like M1 methods or something like that, you have two beams going toward each other. And the thing is that there's only one beam that allows in like M1 methods or even worse flux limit fusion methods, right? And then what happens, in that case, you get like a Death Star-like situation where two light beams intersect and make a single light beam. So the fact that they cross is actually kind of a cool thing, basically, that happens, right? The other thing that we did is GR hydrodynamics, right? So this is for static space-time. The imprep refers to work that's just been about to complete for dynamic space-times, all right? So we're basically about to do GR hydrodynamics in full dynamic spacetimes. And then, of course, we also have MHT, which Logan showed earlier. I'm not sure this movie should work. I'm not sure why it's not working. Anyway, this is just our Alfvén wave, right? So it's nothing too amazing by any means, right? I want to outline, this is the only slide I have left, basically outline some of the features that we have already, okay? We have hydro, self-gravity, entropy or energy conserving. This is basically a reflection of when I first built this thing, I built it based on Volker Springel's repo paper, right? So he had entropy and energy conserving. Most of the time, I just use energy solving. I don't really care about entropy solving anymore, right? Logan and I built multi-stepping and Mesa equation state in 2019. All right. Logan also built basically moving and reactive boundary conditions in 2020 and 2022. All right. We have radiation hydrodynamics in there. We have GR hydrodynamics basically in there as well. There's MHD divergence clean, which Logan is basically finishing up. And Sinead and I have worked on nuclear burning recently, basically to look at TDEs with white dwarfs, right? There's an open source version in June 2022. All right, you might notice that it's almost the end of 2022. That's because it's there already. Okay, you can just actually pull the moving mesh version off of the public directory, and then the other thing I want to try to do in the next few years is basically the moving mesh GR hydro for binary neutron star mergers. I'm about the dog's about to catch the car. I'm not sure what can happen after that. Okay. And then the longer term goals, I also want to do MHT with constrained transport schemes. We'll see how that goes. And then I also have some ideas for higher order spatial reconstruction methods. Right? So thanks a lot.
Okay, and the schedule has us switching to remote now with Vinaya Velson, more manga.
Can you see my screen?
Looks good.
I hope you can still see it. Can you hear me okay? Just confirm.
Yep.
All right. So hi everyone, my name is Vinaya. I'm a grad student working with Phil. So my talk today is on evidences of homologous expansion in common envelope evolution. Earlier today, Logan and just now Phil already talked about using manga in simulating common envelope evolution. So I used the same method to simulate a common envelope evolution system containing a 2 solar mass red giant and a 1 solar mass companion star. At the beginning of the simulation, the system goes into a plunging phase, which ends at around 200 days. And after that, the orbital decay slows down, as you can see here. Considering masses or gas particles with total energy greater than 0 as unbound, we see that in our simulation around 1000 days, most particles become unbound, or in other words, the system ejects most of its envelope. So now we look at evidences for homologous expansion in the simulation. So what is homologous expansion? Homologous expansion is this radially symmetric radial expansion where the radial velocity is proportional to the radius. So on the top left corner, I'm plotting the radial velocity as a function of radius for different time slices from the simulation. And the best fit power law fit for this graph is given as the radial velocity proportional to radius power 0.96, which agrees quite well with our expected relation for the homologous expansion. So confirming homologous expansion in our simulation. Now, combining this relation with spherical symmetry, one can easily show that the density has to be proportional to inverse time cube. So the top right plot shows the average density of our common envelope as a function of time with the black dotted line, the expected shape of the curve. Now we can see that our simulation agrees quite well with the expected shape. Now, we can also see evidences of homologous expansion from the profile of density. So here I plot the density profile as a function of radius for different time slices from the simulation. Now you can see that over time, density maintains a shape, and this region of the curve fit as the density proportional to the radius power -3, which again confirms homologous expansion. So in short, our common envelope evolution simulation shows that the envelope expansion indeed follows homologous nature. And I'll stop there.
Okay, and then our last speaker for the day, Ellie Spalding.
Last one. Hi, my name's Allie. I also work with Phil at University of Wisconsin-Milwaukee, along with the rest of the UWM group, and I focus specifically on tidal disruption events. So a tidal disruption event happens when a star approaches within the tidal radius of a supermassive black hole. Its tidal gravity overcomes the self-gravity of the star, and then the star is ripped apart. TDEs are important to study because they give us new information about distant black holes, such as knowledge about accretion physics for a single black hole. Phil definitely talked about manga more than I will, but that's the simulation code that I use to better understand the expected emission of from TDEs, along with specifically so far, I've really focused on varying the impact parameter of TDEs and seeing how that affects the expected emission. So in the middle there, I just have the same GIF that Logan showed earlier of the moving mesh code, just showing you how the mesh moves and forms with the fluid. And then I have my simulation of a TDE on the bottom, and you can see how about half of the mass accretes to the black hole and the rest is unbound. And then on the right, I have two of the same plots of TDEs, just with different impact parameters. So the top one is a star that approaches farther from the black hole. So that's a smaller impact parameter. And then the bottom is double the impact parameter. So the star is closer to the black hole. Okay, so my results so far, I've focused on two projects, one on the left and the right. So on the left, I looked at how the energy spread relates to the impact parameter of the TDE, which we define as beta on that first plot. And we found that the energy spread of the unbound debris increases with closer impacts. Specifically, it goes as beta to the 1/2. This is important because it affects observables, such as the fallback rate down here. So we found that the peak luminosity time actually shifts earlier with closer impacts. And this was the first result we found that could potentially lead us to using observational data to constrain the impact parameter of a TDE, which is not able to be done yet. And then on the right-hand side, I have my project where I focused on the radio emission from TDEs. I used a synchrotron emission model. So I took the unbound debris interacting with the medium around it and creating that synchrotron emission. And one result we found was that the peak flux shifts to higher frequency for closer impacts. So again, another observational observation we can make that could potentially constrain the impact parameter, now using radio emission. And then lastly, on the bottom there, I used that synchrotron emission model along with flux and frequency observations from radio TDEs. And when you plot them, if you assume that the density around it, the density profile goes as n, goes as a power law there, then you can potentially constrain that density profile after calculating the density, and S is the radius of the emitting region. So thank you.
All right, awesome. Let's open it up to a few questions for our flash speakers. And Charlotte, I see that you have a question. Go ahead.
Hi, thanks. This is for Pedrick. I noticed on the last slide, which you didn't have a chance to talk about, there was some discussion of the shielding length. And I wonder if you could talk a little bit more about your ideas there.
Yeah, thank you, Charlotte. I know you wrote the original script that I've been resurrecting from 10 years ago. So yeah, the shielding length. The shielding factors are dependent on the column density of the gases passing through. And sort of the issue that we're having is, supposedly, in a perfect world where we could model every single molecule in our radiative transfer routine, we wouldn't need these shielding factors. But we can't model every single molecule. We have to abstract with particles. And sort of the question is, to what extent does our radiative transfer routine handle the shielding between particles? Do we need to apply the shielding on like a particle by particle scale? So like each particle just shields itself a bit, or just apply shielding from its neighbors? And if we do it on particle by particle scale, we have some questions about what should the length scale be? Should the length scale be the softening length? There's a Sobolev approximation that uses the local density gradient, or should we use something different? So it's all because we have this column density dependence. And so we need some length scale over which to define these shielding factors.
Okay, sounds like you're still open-minded. Yeah, I look forward to hearing more about it.
Thank you.
Questions? Go ahead, Tom.
It's Tom Quinn. Could I ask more about the physical parameters that this is really interesting. So what was the size of the black hole and the size of the star and all
Yeah.
that kind of
So I do one solar mass black hole, or sorry, one solar mass star, and a million solar mass black hole. And I use a zero-age main sequence star with the adiabatic equation of state.
And so the flux here is assuming it's at the center of the Milky Way or something?
I don't know if we would specify that it's at the center of the Milky Way. Yeah, I'm not sure about that.
Phil, if you want to comment.
Yeah, I'll comment. So Tom, I presume you're asking about that last plot, the AT 2019 DSG. Is that what you're commenting about?
The top plot where, right, the Milajanskis must assume a distance.
Yes. So actually,
Yeah, we used 100 megaparsecs as a distance. And that AT 2019 is at 230 megaparsecs, that observational data. Yep.
Okay, go. Final burning question. Go for it.
All right, this is Michael Tremmel. I have a question for Vinaya about the common envelope simulations. So those are all really cool, and we've heard from a few different people. So I know that phase of evolution is really important in binary evolution. It's always been, at least as far as I remember, pretty uncertain. Have the simulations that you've been running or your group's been running been able to constrain the common envelope phase? The efficiency at which it's able to sap away angular momentum from a binary. Like, has it been progress, or is there still lots of uncertainties in parameters? And if so, where are those uncertainties now? Does that make sense?
Yeah, so my work do not really look into that, and I'm actually not sure if Logan has done anything related to that.
There you go. Hey, Logan here. So a key parameter in the common envelope formalism is what's known as the alpha efficiency parameter, which is the efficiency with which orbital energy is transferred to the envelope, right? And so there's a fairly wide range of alphas that are found by simulations and that are inferred from observations. We find an efficiency parameter of typically around 2, which may seem weird that efficiency is larger than 1. That's because that formalism assumes the energy can just come from the gravitational binding energy, right? But there could be other sources of energy like recombination and thermal energy and whatnot. So another thing that we've found, like with the simulation that Vinaya was showing, was that if you run it long enough for a scale of thousands of days, the entire envelope can be ejected from the system. And that's also been found by some similar simulations in Arepo by, I think, Fritz Roke's master's student.
Okay. With that, let's thank all of our speakers for the afternoon again.